Good morning.
Good morning,
Good
Mr.
morning.
Shaw.
Good morning.
All right. Well, I hope you're all having a good day. Let's see. Who's there? Everyone in Joseph City?
Yes, here.
Everyone in Holbrook?
Is everyone
Tara
there?
is gone.
Sarah? Anyone else? Okay. So tomorrow, tomorrow we're taking the chapter 3 test. All right. So be studying for that. Now, Thursday, we're not going to have a broadcast, and I'm going to ask for your opinion on your opinion, your preference. Would you rather have Thursday be a Moodle day where we do quizzes? Let's see, what did we do last time? So we do quizzes like 4.1 through 4.3 on Thursday, or would you rather have a taped broadcast? So it wouldn't be me live. It would just be a recording of me teaching the next section 4.5. So on Thursday, what would you prefer to do for class? Would you rather take quizzes or watch the next section?
Well, if we
Big
did
quizzes.
the quizzes this Thursday, would we not do them next Wednesday? So like the people that are gone.
No. Next week is a whole different issue. Okay, I'm not going to complicate that. I'll tell you what I'm hoping to do next Wednesday is to have a quiz or two that you can do from your house so that you don't have to come in. That's my plan for Wednesday, and that is regardless of what we do this week. Okay.
Personally, I'd rather take the quizzes.
Okay.
Yeah, there's people going to a tournament and they're not going to have access to a computer at all next week. Because it'll be.
Okay.
Until Thursday.
Well, except Lauren, so now you're talking about next week again? Okay. Again, I don't want to deal with that. But as far as quizzes, you can do those on a smartphone. I really don't think that's an issue. Okay. Okay. So for Thursday, so I'm hearing the majority of you would rather just be a Moodle day and do quizzes and not have a taped lecture. Is that correct? Okay, then that will be the plan. So today we're going to cover 4.4, and then we will, so then tomorrow we'll have the chapter 3 test on the Moodle during class time. Thursday during class time, I will set up quizzes 4.1 through 4.3. And then next week, we are going to have class on Monday and Tuesday. And what I'm trying to do is avoid the day before Thanksgiving. But NBC actually is open that day. And so I'm trying to make it so we don't actually have to come that day. Okay? So I know like Holbrook, actually, aren't you guys, everyone's off next Wednesday, right? So let's try to do something. And so I'll let you know exactly what we're doing. I guess those guys that are going to be gone, just look for the quizzes that are open. I mean, you can take them anytime. You can take them. Now I've got to figure that out. If how I'm going to do that. If I'm going to have that quiz open for a couple of days. That's next week. I'll figure it out. Okay, so let's go ahead and get going on this 4.4. All right, so So this lesson is on the fundamental theorem of algebra. And if that sounds like it ought to be important, it is. It's maybe the biggest idea, or what we get from this is a big idea in algebra about zeros. So we're going to talk about that. Yes?
We don't have our papers yet. They're being printed right now.
Okay. All right.
Yeah.
You don't.
Okay. So the fundamental theorem of algebra, I'll just tell you right now, the big idea that we're working toward, and that is that whatever the highest degree of your polynomial, that's how many factors. That's how many zeros you have, okay? And so we'll kind of talk about that. We're also going to talk about multiple zeros and how they affect the graph, the geometric meaning, and conjugate pairs of zeros, complex numbers. Okay, that's kind of what we're going to do today. All right, so the fundamental theorem of algebra, it says that you're guaranteed to have at least one zero. Okay, so that's kind of actually a little bit weak, because it's then we develop other theorems and stuff from the fundamental theorem of algebra, but we start off with the idea that we know we are going to have at least one zero for any polynomial of degree in greater than or equal to 1. Okay.
Mr. Strong, I have
Yes.
a question.
Okay, go ahead.
When you say the highest degree is the number of zeros, is that including the imaginary zeros?
Yes, that's what we're going to be building toward, is that so we start off with at least one, but then when we start including all the multiples, all of the complex ones, then we have exactly what that number is. Okay? So
Okay.
we just read the end of the book there. I mean, that's the big idea. Okay? So I'm glad you asked that. Now, and this isn't really in your notes here, but the idea is that whatever number of zeros that you have, for every zero you can do a factor. So if 3 is a zero, x minus 3 is a factor. And so however many zeros that you have that many linear factors. All right, now, multiplicity of zeros. So let's say if you have a factor that occurs twice, x minus 3 squared, then we say that 3 is a zero of multiplicity 2. So the multiplicity that means how many times it occurs, okay? Now the way that you write that, if 3 is a zero and it has a multiplicity of 2, you write down 3 as a zero and then you put 2 in parentheses. So it doesn't mean 3 times 2 here. It means 3 occurs twice as a zero, okay? Okay, so Joseph said, you guys just write down those 4 words for a minute, and then when you get your papers or whatever, just copy it in. So if P is a polynomial of degree n, then P has at least 1 zero. So that's where we're going to start, okay? All right. So it says confirm that the second degree polynomial function x squared plus 8x plus 4 has at least 1 zero. All right, so how would you do that? How would you prove that it has a zero?
Factor?
Okay, you could factor and solve it. Set it equal to 0 and solve. What's another way?
You do the factors of the constant over the factors of the leading coefficient.
Yes. Excellent. What's another way?
Can't you just look at the highest degree?
Okay, so So this degree is telling us, since it's a polynomial of degree 2, that we should have 2 zeros if we include the complex ones and multiplicity. Okay? So let's look at a couple of other ways. So here, factoring would get us 1. Also graphing. If you graph it and it touches, then that's considered a 0. Okay? And so here, we would have a 0 of -4, and it actually occurs twice. -4 and -4. So we would say that this has a multiplicity of 2. There's 2 zeros here. Okay? But they're the same thing. And so, yeah, whatever the exponent is, that's really going to be the number of zeros. But that's including multiplicity and the complex numbers. Okay? Any questions on that? Okay, so the graph of an nth degree polynomial function has at most n x-intercepts and at most n minus 1 turning points. So like the hilltop and the valley, those are our turning points where it changes direction. So if you have x to the third, if you have a third degree polynomial, that means you could have up to 1, 2, 3 zeros and 2 turning points. Okay? So n zeros and n minus 1. All right, so for this one, how many zeros could you have? 4. And how many turning points? 3. Okay? All right, so write down the maximum number of zeros and turning points for this. All right, so Taylor, what's the maximum number of zeros here?
3.
3.
And turning points?
2.
2. Okay? Everybody okay with that? Okay. Multiple zeros and their geometric meaning. Okay? So if k is greater than 1, if k is the multiplicity, okay? So when we're talking about it occurs k times or 2 times, 3 times, whatever, okay? Then to determine what's going to happen to the graph, you determine if k is even or odd. So if the number of times it occurs is an even or an odd number, okay? If a polynomial function f has a repeated 0, x equals 3, with a multiplicity of 4, okay? So when I talk about even or odd, it's not the 0 itself, it's the multiplicity number, okay? It's that it occurs an even number of times. So if it occurs an even number of times, the graph of f touches the x-axis at that point, x equals 3. If f has a repeated 0, x equals 4 with a multiplicity of 3, okay, so when we talk about even or odd, it's not the 0 itself, it's the multiplicity. So here the multiplicity is odd, and so if it's odd, then the graph of f crosses the x-axis at x equals 4. Okay, now, there used to be a TV show called The OC, and I used to make this big deal about E.T. at the OC. And it turned out that my students didn't get it anymore because none of them have ever seen the movie, the show The OC. So, but it's still a way to remember even touches odd crosses. E.T. OC. Okay? And that will help us as we look at the graph of these things. Okay? All right. So, for example, let's say I wanted to graph this. Okay? All right. So, the first thing you do is figure out the function dance for the end behavior. Okay? So, so if you imagine looking at the x's, if you cube that out, x cubed, and it's positive, that's going to be odd positive. So what's the function dance move for odd positive? Okay, so odd positive, positive right arm up, left arm down. So that's the end behavior. Okay, then you graph your 0 here, which is 1. Okay, so you start with the end behavior, you graph your 0 at 1, and since the 0 occurs an odd number of times, the graph crosses through that point. Okay? So you do the end behavior, you do the zeros, and then you figure out if it touches or crosses at that point. Okay? All right, so let's see if you can do practice 2. Not that one. This one. Okay? All right, so see if you can graph it without a calculator. You're just going to start with the end behavior, graph the zeros, and then determine if it crosses or touches at each one. All right, so Madison, if you multiplied this out, x would be to what power? What's the degree of this polynomial? I mean, I really don't want you to multiply it out. I just want you to just focus on the x's and say, what would x would be to what power?
Would it be 6?
It would be 6. So because you have 1 to the first, and then to the second, to the third, and so if you add those up, you're going to get x to the 6. So, and it would be positive. So even positive. So what's the end behavior, everyone, for even positive? Okay, so start your graph there. So start both ends going up. Okay? Now, the zeros. All right, Serena, what are the zeros here?
-2, -1, and +3.
That's correct. So put dots at those points on the x-axis for your zeros. At -1, or -2, -1, and +3. So so let's say going from left to right. So it goes up, starts up. Okay? Now the first 0 from left to right is negative 2. All right, so if you think the graph crosses at negative 2, I want you to hold up a C. If you think it touches, then do a T. Okay? All right, so at negative 2, tell me, does the graph touch or cross at that point? Okay? Yeah, because it just occurs once, so odd crosses. Okay? So it's going to cross and come down and then come back up and then go to the next 0. Now, you don't know how far down it's going to go. We don't worry about that. Okay? We'll worry about that in calculus. All right? We'll figure that how to know where to turn around. So the next one would be, okay, so at negative 1, does it cross or touch? All right? You're right, it touches. So at negative 1, you come up and it just touches and then it just goes back down. Okay? All right? Then it's going to, you come to go down however far you want to go. Okay? We're not worried about that. Then we're going to come back up and the last 0 is at 3. Okay? So crosses or touches at 3. All right. It's going to cross because 3 occurs an odd number of times. And so odd crosses. So it's going to come back up and it's going to look something like that. Now again, we're not worried about this, and if that's not perfect, we don't care. What we're wanting to have accurate is the end behavior, and then if it touches or crosses at each 0. Okay? Now, a kind of a way to check this is that, like, let's say that you got to this last one and you thought maybe it would just touch and come back down. Well, see, then that wouldn't work with the end behavior because you know both ends have to go up. So if you had that and you thought, oh, it just touches and go back down, well, then somewhere you've messed up. And so you'd want to go back and redo the problem because it's got to match up with the end behavior, with the function dance. Okay? All right. Any questions on that? All right. So let's go through this one together, okay? So what is the end behavior for this one? Both ends up. Even positive. Okay, 4, 5, 6, 7, 8. So it's x to the 8th. Okay, what's the y-intercept? Let's say we want to make the graph more accurate, so we want to graph that point. How would you figure out the y-intercept? How do you figure out the y-intercept?
You set x equal to 0 and solve for y.
Okay, so if we plug in 0 for x here, here, and here, what would we get? Can you do that in your head? So 1 to the 4th times negative 2 to the 3rd times negative 1. What would you get?
Would it be positive 8?
It sure would. Okay. All right, very good. All right, so now what are the zeros here? Just call it out.
Just do.
Wouldn't it be -1, 2, and +1?
Correct. And so -1 occurs how many times?
Once. Oh wait, no, 4. Sorry, because of the X.
4 times. So you would want to write it like that. So -1 occurs 4 times. All right, and 2 occurs how many times?
3.
3. And then 1 occurs
Once.
just once. Okay? So you go by the exponents on the factors. Okay? All right, so just on the side on your paper somewhere, your notes, see if you can graph this one. Don't use your calculator unless you just want to check your final answer. But I want you to try to do it without the calculator. All right, let's see what you've got here. Okay, so both ends up. You've got these zeros, and it touches the first one, crosses the second one, crosses the third one. Okay, from going from left to right. And then notice that the y-intercept 0, 8, we did graph that point so that it would be a little more accurate. Okay. All right, any questions on that graph or any of that?
So when you're going to graph, you put the numbers in order from least to greatest, correct?
Wait, say that when you're going to graph, you put what?
The numbers in order from least to greatest, so like
Yeah.
the -1, and then you go to 1 before the 2, correct?
Yeah. Yep. All right. Any other questions? All right. Great job, everyone. Okay, next, conjugate pairs of zeros. In the complex number system, every nth degree polynomial function has exactly n zeros. So if you can include the multiplicity, you include the complex, that's how many zeros you have. Okay? Exactly n. So whatever the exponent is, that's how many zeros you're going to have. But you need to realize that the complex zeros don't show up on the graph. Okay? So you might say, oh, I'm going to have 4 zeros and maybe only 2 of them show up on the graph. Okay? That's okay. The complex ones don't show up. Okay, the next one, if a plus bi, this is the conjugate roots theorem. If a plus bi, where b is not equal to 0, is a 0, then so is a minus bi. So that means that if you know any complex root, then its conjugate also must be a root or 0. Okay. So it says given 3 minus 2i is a 0, factor this. Okay. Now you've probably never factored a polynomial that big in your life. Okay. And I know how much, like Lauren loves factoring already. So now we're moving up to the next level of factoring. Okay. So my first question is if 3 minus 2i is a 0, what also must be a 0?
3 plus 2i.
3 plus 2i. So if you know 1, you know 2, if it's a complex number. And so that's kind of nice. Now, there's 2 ways to do this problem, okay? And I'll show you the first way is to say, okay, to figure out what the polynomial would be that would have those 2 zeros, okay? And so what I'm going to use, and this is actually how I would do this problem, is say, okay, if 3 plus 2i, 3 minus 2i, 3 plus 2i, if those are the zeros, then to get the polynomial, I would use this little formula, x squared minus the sum of 2 zeros plus the product. That's going to give me the polynomial. So I have to add these together and multiply them together. So when I add them together, the I parts cancel, and I just get 6. When I multiply them together, then I end up with 9 minus 4i squared. So that's 9 plus 4, which is 13. So their sum is 6, their product is 13. So then I put that up there, and so that's the polynomial that would have those 2 zeros. So now what I do is use polynomial division to get the other polynomial. That what I would multiply x squared minus 6 plus 13 by. So I take my original polynomial and divide by x squared minus 6x plus 13 to get it. And then whatever I have left is the quotient. Then I need to factor that to get the last 2 zeros. Okay? So why don't you see if you can finish it off here. So you're going to use polynomial division here, and then whatever you get for your quotient, for your answer, you need to factor that and find the last 2 zeros. Okay, so Anna, what do you get for the quotient?
I got x squared minus 3x minus 3.
Let's see. How about minus 4? Let's go through it. Why would it be 4?
Negative 3x 13.
Okay, so here you get 14x squared minus 18x squared, so it's going to be negative 4x squared. So then when you say what times x squared is negative 4x squared, it's going to be minus 4. So somewhere you did that subtraction wrong. Okay? So double check that. And notice it should divide in evenly, no remainder. Because we got those are factors. So if you ended up with a remainder, that's another clue that you messed up. Okay? All right, so any other questions on the division? Or anyone need me to go through it? Yes. Andres, do you have a question or you want me to go through it?
I was just stretching.
Oh, okay.
Can you go through it for me, please?
Sure. So you look at the leading terms and you say what times x squared is x to the 4th? And so it's x squared. So now you multiply through and you get x to the 4th minus 6x cubed plus 13x squared. Change the signs, boom, boom, boom. This goes to 0. This goes to negative 3x cubed. This goes to 14x squared. Bring down the negative 15x. Look at the leading terms again. What times x squared is negative 3x cubed? It would be negative 3x. So you multiply through and get negative 3x cubed plus 18x squared minus 39x. Change the signs, boom, boom, boom. This goes to 0. This goes to negative 4x squared. Let's see, negative 15 plus 39 is 24x. Bring down the negative 52. What times x squared is negative 4x squared? And that's your negative 4. So you get negative 4x squared plus 24x minus 52. Change the signs, boom, 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 and everything cancels. So you just get 0 as your remainder. All right, so now to finish up the problem, we need to factor that. X squared minus 3x minus 4. We need to factor that and get the last two zeros. All right, so Desiree, what does that factor to?
X minus 4 and then x plus 1.
Okay, and so then the zeros will be what? So these are the factors. What will be the zeros?
Positive 4 and negative 1.
Positive 4 and negative 1. And so, and then we have the 3 plus or minus 2i from the beginning, and then the last two that we found. Okay? So if the question asked for the zeros, actually this didn't ask for the zeros, so you didn't have to do that red part. Okay, the factoring, the x minus 4, x plus 1, and then the with the complex zeros, see it's x minus each factor. So x minus 3 plus 2i, x minus 3 minus 2i. Now you might see the answer written like that, or sometimes they'll go ahead and distribute the negative through. But I like that answer. I actually like the second to the last answer, right here. So where you take each of your zeros and the factor is x minus each zero. Okay? So if it asks for the factors or the zeros, you do the same thing. Okay? You've got to break it down term by term. Okay? The other way that you could do it, but I'm not going to go through this, but if you're just a whiz at synthetic division, you could put in your complex zeros in the magic box. You plug in 3 plus 2i and do synthetic division, and 3 minus 2i and do synthetic division. But I found that most students make more mistakes that way. So I would just say, find the polynomial that has these two zeros using this formula, and then use polynomial division and break it down from there. Okay? Okay, we got that already. Okay, so let's say I'm told I want to write the polynomial that has zeros of 3, 5 occurs twice, and then I. Okay? Now, what's tricky about this that a lot of students would miss?
Is it that the I is one I?
So 1i. So if I is a 0, what also must be a 0 that's not listed?
Negative I?
Negative I. And so this is a problem of deception. I'm warning you right now that if they ever tell you a 0 that's complex, you know that the complex conjugate must also be a 0. So then you say, okay, then the factors are x minus 3, x minus 5 occurs twice, so you do the squared, and then x minus I, and then this would be the one that a lot of students would miss. Because it's x minus a negative I, which would be x plus I. Okay? So that's the factoring.
Mr. Strong,
Yes.
so when you say a conjugate, what if it has like more than just x minus something? Like if one of the factors is more, it has like
then you simplify it. So like if it's 3 plus 5i, the conjugate would be 3 minus 5i. Now if you had like 2 plus 3 plus 7i minus 4i, then you simplify all that. And then take the conjugate. You just change the sign in the middle. Now, this is just fine for me for a final answer. But when you check your answer in the back of the book or something, let's say there's a book problem, sometimes they'll multiply everything out. Okay? But this is fine for me. All right? So see if you can do practice 3B. And you don't have to multiply it all out. So Ricky, when you've got it.
That's it. X minus 2, x minus 4, x minus 2i, and x plus 2i.
That's it. Very good. Okay? Any questions on that? All right, so can anyone tell me why you can't use a graph to locate complex zeros?
They don't fall on the x-axis, so you
Yeah,
can't.
they don't show up. They're not on the graph. So that's why the calculator is a great help for finding the zeros, but it's not the perfect tool. Okay, because you can't find the complex zeros that way. All right. Well, so that's it for 4-4. Were there any questions or any of the blanks that we missed? All right. Well, I want to go ahead and start 4.5. So I want to make sure we're able to finish it next Monday. Okay, so in this section is on rational functions and rational inequalities. The part about the rational functions, this part is really important in calculus as we start graphing and so on. Okay, so what a rational function, remember, that's where you have a ratio of two functions. So you could have a polynomial in the numerator and a polynomial in the denominator. So ratio.
I think you might have sent us the wrong notes because we have a packet that is all of the stuff that's on the board, like in all of your writing. We don't have the stuff we usually have.
So I think you sent us the presentation instead of the guided notes. Unless that was on purpose.
That'd be funny.
Because we have a big old packet with like 7.
Okay, well, that's totally my mistake.
don't have anything.
Well, actually, that would be helpful to you at some point. Yeah, you can see the notes. I'll resend the guided notes. Yes.
Holbrook doesn't have any of 4.5.
You don't have any 4.5? Okay. All right. Well, okay. So let me just kind of introduce it without giving any notes. Okay. So no notes. Don't write anything. Just look, and it'll make it a little easier when we see it again. Okay. What we're going to try to do is graph stuff like this, where we have vertical and horizontal asymptotes. Now, the dotted lines are not part of the graph. They don't show up on the calculator, but we're going to try to find them anyway. Okay? So those are the asymptotes. All right. So basically when we look at a vertical asymptote, what makes a vertical asymptote is when you have a zero in the denominator. So we'll just look at a function and say, what would make that denominator go to 0? And if it's x equals 2, then at x equals 2, we're going to have a vertical asymptote. So those are pretty easy, okay? The vertical asymptotes. And so that's going to be similar to the domain, because whatever would make the denominator go to 0, that's going to cause a vertical asymptote, and that's going to be thrown out of the domain. Now, the horizontal asymptotes are a little bit more complicated, But this is where this part, when we go through this, is going to be extremely helpful in calculus. And so we'll do a little test for horizontal asymptotes, and then we have what we call slant or oblique asymptotes. All right. Okay. So what values for x would make that denominator go to 0? 3. Any others? And -3. So it is possible that you could have more than one vertical asymptote. And so we'll see that. So any values for x that would make the denominator go to 0. Okay? All right. So we'll just stop right there. That's a good little intro. And then I'll resend the notes before Monday. And then we'll try to finish this up on Monday on 4.5. Okay?
Thanks, Mr. Strong.
You bet. You guys have a good weekend. Good luck on your tests. Now, believe it or not, by the way, that this is the last section in chapter 4. So chapter 4 test is going to be coming after Thanksgiving. Anyway, so, okay? All right. Well, you guys take care. Have a good one.